Hey, thanks for tuning in. Welcome to Nomadic Geek. Are you tired of losing your valuable sensor data and wish you could store it securely over time for future analysis? Or have you ever dreamed of designing a stunning dashboard to visualize and make sense of your sensor data through interactive graphs? Well, you're in luck. Because in this episode of the Geeky Surveillance System tutorial series, we'll guide you step by step on how to store your sensor data from our modules and create captivating visualizations. Get ready to embark on this journey to unlock the full potential of your IoT devices. In our previous videos, we've set up sensors and ESP32-CAM modules to string data to our Node.js server via WebSockets and optimizing the code for maximum efficiency with cluster multithreading. If you haven't checked out those videos, I highly recommend you do so, as this tutorial builds upon that foundation. Although it's not essential for understanding this video, watching them afterward will provide valuable context. As someone who wants to monitor data like temperature, humidity, and battery usage patterns in my van and analyze them over time, I need an effective way to visualize these changes. That's why, in this episode, we'll dive into the world of data visualization and explore how to create a web browser dashboard with interactive graphs that display our stored sensor data in a user-friendly manner. So, let's get started on this exciting adventure. If you like this video, don't forget to give it a thumbs up and hit the subscribe button and notification bell so you know when I post more content. If you have any thoughts, questions, or feedback, please don't hesitate to share them in the comments section below. Stay tuned, and let's get started. A database is a digital storage system designed to organize, manage, and retrieve structured data efficiently. They come in various types, such as relational, NoSQL, or graph databases, each tailored for specific data models and use cases. To interact with the data, databases use query languages, like SQL for relational databases, or specialized APIs for NoSQL databases. The primary purpose of a database is to store information in an organized manner, allowing for seamless data retrieval and manipulation in various applications. MongoDB is a popular NoSQL database designed for handling large amounts of unstructured data. Unlike relational databases, which use tables and strict schemas, MongoDB employs a flexible, document-based model using JSON-like objects called BSON. This flexibility allows for easy storage and querying of complex data structures, such as nested arrays and documents, making it ideal for handling diverse, hierarchical, or evolving data requirements. MongoDB is scalable, high-performing, and widely used in applications that require a more dynamic and versatile approach to data storage and management. Chart.js is a popular JavaScript library used for creating interactive, responsive, and customizable data visualizations in web applications. It enables developers to easily generate charts and graphs using the library's extensive collection of built-in visualization types, such as line, bar, pie, and scatter plots. By providing a simple API, Graph.js allows seamless integration with your web application's data, empowering users to explore and make sense of their data in a visually appealing and intuitive way. First, we need to install MongoDB on our system. Go to the website and scroll down. Ignore the Atlas version and continue further down to choose your system. Then, click the download button. After downloading MongoDB, locate the installer and open it to begin the installation process. Choose the option Run Service as Network Service User. Be sure to select the Install MongoDB compass. While not strictly necessary for this tutorial, it can be a useful tool to check that the data is being properly written to the database. Click Install. The installation process may take some time, but once it's complete, we can start using databases in our projects. We start by examining the changes in our package.json file to see what we have added. As mentioned earlier, MongoDB is a popular NoSQL database for managing large amounts of unstructured data. Mongoose is an object data modeling library for MongoDB and Node.js. It provides a simple, schema-based solution to model your application data, making it easier to work with MongoDB in a Node.js environment. By including Mongoose, you can use its features for validation, querying, and data manipulation. We've also included the .env package in our project. .env is a useful tool that simplifies managing application configurations by centralizing them in a single file. This makes it easy to modify settings without digging through the codebase, and it provides a convenient way to separate configurations from the main application, promoting maintainability and security. By using .env, you can effortlessly adjust configurations as needed, keeping your application flexible and adaptable. Here, we can observe several settings that have been moved from the codebase to our .env file. These include the client HTTP port, the WebSocket port for client connections, the frequency at which sensor data is updated, in this case, once every 150 milliseconds, as well as settings for object detection frequency and score threshold. Additionally, we have MongoDB settings such as the database name, IP, port, and maximum pool size. First, let's take a look at the server.js file. In the section where we include libraries, not much has changed, but two important lines have been added. We have the .env. This line enables the use of the .env configuration file and integrates its functionality into our project. Next, we've included the sensor model. Let's take a quick look at it. First, we include the mongoose.config.js file. We'll take a closer look at this file after we've reviewed the sensor model file. Here, we define the mongoose schema for our sensor data. The schema, called sensor schema, specifies the structure of the data we'll be storing in our MongoDB database. This makes it easier for us to interact with the data and ensures consistency across all sensor entries. Here's a breakdown of the fields in the sensor schema. Sensor ID. This is a required field of type string, representing the unique identifier for each sensor. Timestamp. This field is of type date and is set to the current date and time by default, using date.now. Temp, hum, CO, LPG, and smoke. These fields represent different sensor values, such as temperature, humidity, carbon monoxide, LPG gas, and smoke levels. They are all of type number, and you can add more sensor values to the schema as needed. With this schema in place, we can now manage our sensor data more effectively and ensure it follows a standardized format when stored in the database. This function, getAllSensorsData, is an asynchronous method defined as a static method on the sensor schema. Static methods are functions that belong to the schema itself, rather than to instances of the schema. The method retrieves all sensor data from the database. It uses Mongoose's find method with an empty object, which means it doesn't apply any filters to the search. The function then returns an array of all sensor records. If an error occurs during the process, it logs and rethrows the error for the caller to handle. getAllSensorIDs is another asynchronous method that retrieves a list of unique sensor IDs from the database. It defines an aggregation pipeline with two stages, $group to collect all unique sensor IDs, and $project to remove the _ID field and create a new field named sensor ID. The function then executes the aggregation using Mongoose's aggregate method and returns an array of unique sensor IDs. It handles error in the exact same manner as earlier function. getSensorData by ID, yet another asynchronous method, fetches sensor data for a given sensor ID from the database. The function uses Mongoose's find method to query for data matching the provided sensor ID. It then returns the retrieved sensor data. The getSensorData by ID between timestamps function provides a more targeted approach to data retrieval. By specifying a sensor ID, start time, and end time, it returns sensor data within the defined time range. This function is particularly useful when you want to analyze sensor data from a specific period. As always, if an error arises, it logs the details and rethrows the error for further handling. The Save Sensor Data function adds a delightful twist to our sensor model, the ability to store sensor data. It accepts the sensor's object as input, and through the create method, stores this data in the database. Upon successful data storage, it logs a celebratory message. However, if an issue arises, it logs the error and rethrows it for proper handling. The function then resolves to true as a final touch. This part of the code creates a new Mongoose model called sensor using the previously defined sensor schema. Then, the Mongoose instance and the sensor model are exported, making them accessible for use in other parts of the application. Now, let's take a look at the mongoose.config.js file, which we included at the top of the file. First, we import the Mongoose library, which will help us work with MongoDB. We then include .env to manage our environment variables, making our app more flexible and using the settings we defined in the .env file shown earlier. We set Mongoose's debug mode to false to reduce unnecessary console output. Next, we use the Mongoose Connect function to establish a connection to our MongoDB server with the specified options taken from the .env settings. Once connected, Mongoose logs a confirmation message to the console. If an error occurs during the connection, Mongoose will log the error details for us. When the connection is closed, Mongoose will also let us know by logging a message. Finally, we export the configured Mongoose instance to be used throughout our application. Back in our server.js file, we have added commands that can be listened to from web clients. We have added two operations sent through WebSocket messages. GetSensor IDs. When a message with the GetSensors operation is received, the server queries the database for unique sensor IDs using the sensor.getAllSensorIDs function. It then logs the retrieved sensor IDs and sends them back to the client through a WebSocket message containing an operation field set to send sensors and a sensor IDs field containing the sensor IDs. GetSensor readings. When a message with the GetSensor readings operation is received, the server extracts sensor ID, start time, and end time from the data.command. It then queries the database for sensor data between the specified timestamps using the sensor.getSensorData by ID between timestamps function. After logging the sensor data, the server sends it back to the client in a WebSocket message containing an operation field set to send sensor readings and a sensor data field with the sensor data. All this will be more clear when investigating the client-side code further on. In sensors.js, we have the same inclusions, .env and sensor model. All other inclusions are the same as in the last video of this tutorial series. Then, all there is left to do is to utilize the Save Sensor Data function within our sensor model, as previously discussed, to persistently store sensor data in our MongoDB database. In the client.js file, which serves as an interface for every connected web browser client, numerous modifications have been implemented. Specifically, Client 2 has been designed with the sole purpose of displaying stored sensor data in graphical format, as evidenced by our file tree and server.js roots. As opposed to Client 1, which undertakes a broader range of tasks, Client 2 has been customized to fulfill the specialized requirements of graphical data presentation. First, we create a WebSocket connection to the WebSocket server. Next, we create several HTML elements. These include a drop-down menu for listing all sensors that have data in the database, 2 date-time picker inputs for selecting start and end times, and a button for getting sensor readings. We then create a div element called controls wrapper and append the drop-down, date-time pickers, and button to it. Following that, we create a canvas element for rendering the chart, and we append the controls wrapper and the canvas elements to the main wrapper div that is already present in the HTML. Now, we set up an event listener for when the WebSocket connection is opened. When it opens, we send a connecting message to the server and request the sensor IDs by sending a getSensors message. Next, we define an onMessage event for the WebSocket. When a message is received from the server, we check the operation type in the data, send sensors or send sensor readings, and call the corresponding function to either populate the sensor drop-down or update the chart. We add an event listener to the Get Sensor Readings button. When the button is clicked, we retrieve the selected sensor ID and the specified start and end times. We then send a Get Sensor Readings WebSocket message to the server, including this information. The Populate Sensor drop-down function takes an array of sensor IDs and adds them as options to the sensor drop-down, allowing the user to select a sensor. Finally, the Update Chart function is responsible for taking an array of sensor data and using it to create a line chart with multiple y-axes, one for each sensor value: temperature, humidity, CO, LPG, and smoke. The chart is created using the Chart.js library, and if a chart already exists, it is destroyed and replaced with the new chart. Now, let's take a look at what it looks like. I'm starting the server up. We can directly see that a sensor I have connected is sending sensor values to the server and that the server is successfully saving them to the database. In the top right corner, I have client 2 for the graphs, and in the lower right corner, I have the standard client which displays all the camera feeds as well as real-time sensor data. Let's choose some dates as start date and end date so that we can view the stored data for this particular sensor module. In the console, we can see that it fetches all the data points, and in the Client 2 browser, the graphs are shown. We see temperature, humidity, CO, LPG gas, and smoke. So, let's take a look at how it all fits together. To make it clearer, I will go through the entire flow, from drawing the graphs to the stored data in the database, and from storing data from the sensors to the database. We'll begin with the client.js file. The update chart function retrieves sensor data from the server through a WebSockets call, and it's used here to draw the values to the graph. These messages are sent from the server.js file, so let's take a look at that. When it in turn receives a message from the client, it fetches the data from the database and returns it by calling the client and triggering the onMessage function in the client. So let's take a look at the getAllSensorsIDs function in the sensor model. We fetch the data depending on the sensor ID. Let's open MongoDB Compass, which we installed along with MongoDB. We connect. Our database is test2, as we stated in the .env file. Here we can see all sensor data stored in the database. We can display the records in any way we prefer by clicking the buttons. Back in the code, let's open the sensor.js file, which represents all of our sensors. As you may recall from an earlier episode, each sensor has its own instance of this file on the CPU thread cluster. If you haven't seen the episode on multithreading, I highly recommend watching it after this video. We call the Save Sensor Data function on the sensor object, which, as usual, resides in the sensormodel.js file. This function creates the record. This concludes this episode of the tutorial series. If you enjoyed what you saw, make sure to hit the subscribe button and give this video a big like. That way, you'll never miss a single one of my future uploads. And if you have any ideas for topics you'd like to see me cover in the future, drop a comment below. Your feedback and suggestions are always appreciated. So until next time, farewell and keep on learning.